Hey everyone, my name is Remy, and I've been working at Oculus for around like 5 years now. And the main things I work on at Oculus is GPU things. So from the actual graphics engines, Unreal 4 and Unity, to the tools, which is what we're going to be talking about today, and through the operating system as well. And what I want to talk about today is GPU profiling. So how to really ask the GPU how it's doing, how to understand applications bottlenecks to bring the visual quality of your applications and their performance to the next level. So what is the current state of profiling? So before we add anything to it, I did want to do like a quick review of what people usually do right now. So you can ask the operating system right now to give you a bunch of system metrics. So the first well-known one is frame rate, but there's also others that I'll go through later. And what the usual framework is to use those system metrics to go then do A/B testing of your materials and assets. So for example, if you know that a scene is running at 72 frames per second, which is the goal on Quest, then you would add like a beautiful statue, for example, and then your frame rate would drop to 45. And then you would be like, well, I probably need to go optimize my statue mesh or my statue shaders. This is quite slow, and then to go to the next level, people will usually use either in-engine profilers or RenderDoc to get draw call timings. So then you could kind of get a breakdown of the length of every element of your scene. The problem here is that this is all what we call top of API. So you would never ask the GPU things directly. You would just ask OpenGL, what is the time of this operation? But you would kind of consider the GPU as a black box that you don't really understand. And so you would make changes on your side and see how the black box reacts without really good communication from you to the black box. And this is what we're going to talk about today. So if we do want to go over the system metrics quickly, the system metrics you can get from, for example, Android Logcat, but there's other ways to get them, such as the in-headset heads-up display called OVR metrics tool. But they're always the same. And the main one is a frame rate. So you have the actual application frame rate, which is this FPS equals 72 here, which just means that your application is running 72 frames per second, which is good. But then there's also other type of frame rates. The two here that I want to talk about quickly were the early frames and stale frames. So in our latency system in Oculus Quest, we give you what we call 2 frame times to complete CPU render thread and GPU execution. So since we are targeting 72 frames per second, a frame time is around 14 milliseconds, and we give you 2 frame times to complete CPU plus GPU. That way you can have full parallelism between the various SoC components, and you can effectively get the maximum performance out of the SoC. An early frame, so here this application has 29 early frames, means that you didn't actually need 2 frame times, you only needed 1. And that Time Warp noticed that after the first 14 milliseconds, your frame was actually ready. So you're going much faster than you should, which is good, but you understanding that is a good thing since you're trying to optimize and maximize your SoC performance. Stale frames is kind of like the opposite of an early frame. A stale frame means that when Time Warp wanted to composite your frame, and so at the end of those 2 frame times, it started looking at if your application frame was ready by looking at a GPU fence. The GPU fence told the Time Warp, I'm still working on this application, on this frame, I can't give it to you. And this would be a stale frame. That means that Time Warp is asking for your frame's not ready, and so Time Warp needs to take the previous frame and reproject it, which is effectively what we call a frame drop, and so your application frame rate is now dropping. And so the stale metric is this: how many frames in the last second you dropped. Then we have foveation. So foveation here is calling out 0D. So foveation 0 means that we're not using foveation at all. So foveation in this case is fixed foveated rendering, which will lower the application pixel density on the sides in order to focus the GPU time in the middle. And D is that you're using dynamic foveation, which means that the foveation level will automatically for you rise and drop as our system figures out that you need the help or not based on stale frames and GPU utilization. Then we have GPU and CPU frequencies. So here it's 2/4, meaning CPUs at 2, which on Quest is 1.6 gigahertz, and GPUs at 4, which is 670 megahertz. So this is actually quite important for application performance because application performance is only valid for a certain clock frequency. So for example, your application might hit 72 frames per second at maximum GPU clocks, but if you start being dropped at like half GPU clock, so this would be around 320 megahertz, you're probably not going to hit 72 frames per second. So it's important to like understand how you are performing according to the clocks that you're running at, because if you change the clocks, you change everything. Then we have a bunch of system GPU times and layers. So here Time Warp is running at 3.2 milliseconds, and your app is running at around 9 milliseconds of GPU time. The reason why we ask you to understand time warp is because time warp needs to run. Time warp is the window manager, so it's what's going to take the application iBuffers and draw them onto the actual screen. So time warp absolutely has to run, and time warp therefore runs on a high priority GPU context. So whether you like it or not, time warp is going to take away from some of your application's precious GPU time in order to do its job. So the more expensive time warp is, the less time your application actually has to really draw. And then we have Guardian here, which is GD at 0 milliseconds, so that means Guardian's off. But Guardian also is considered high priority because you absolutely need to know when you're going to run into a wall. And then we have layer counts too, and then we have pretty standard CPU and GPU utilizations. So this is what you actually get out of the OS right now. Before we really get into what the new stuff that we worked on this year in order to make you understand better what the GPU is doing, I did want to do a quick rehash of the type of GPU that we're running on today on Quest. So unlike a PC GPU, which we call immediate mode GPUs, on mobile we run what we call tile-based GPUs and tile-based renderers. So what that means is that unlike a PC GPU and unlike most GPUs, where effectively as soon as the CPU starts submitting draw calls, the GPU pretty logically would start computing the draw calls. This is not actually what happens at all on mobile. On mobile, we're going to wait for every single draw call for that frame to be submitted before the GPU starts doing anything. And then what it's going to do is it's going to batch all those draw calls together and execute what we call the binning pass, which is executing a small subset of the vertex shaders for those draw calls to figure out where in the screen they go. And then we're going to split the texture that you want to render, such as usually the iBuffers. We're going to split it into what we call tiles. So the tile size differs based on MSA levels and color bit depth and stuff like that. But effectively on our Qualcomm 835 SoC, on the Snapdragon 835, the tile size is usually around 150 by 150 pixels. So when you're rendering your frame, we're going to split that frame into 150 by 150 subparts, and then we're going to figure out which draw calls affect which subparts. So if you have your hands draw calls, usually they're not going to affect the top left tiles because your hands are usually at the bottom right. And then per tile, we're going to compute the tile in very fast GPU tile memory, and then store that in RAM. Then compute the tile, store that in RAM. Compute the tile, store that in RAM. So if we were to look at this on a timeline, this is approximately what it will look like. You would have the CPU render thread at first with no GPU parallelism whatsoever. How the CPU and GPU parallelism works usually, because obviously we don't want to have the GPU just stalling until the CPU is done, is that we're going to do a frame-to-frame parallelism. So you're going to have the CPU running the new frame, and while the CPU render thread is executing all the draw calls for the new frame, the GPU is still computing the last frame. This is how we hit both high GPU and CPU utilization at the same time. And when the CPU render thread is done, then the GPU starts actually doing the work. And so per render pass, so per texture that you're rendering, we're going to do binning, which is this operation of figuring out where, which tiles are being affected by which draw calls. And then per tile, we do render, store, render, store, render, store. And then when everything is stored, then we can actually access the final texture in RAM, and then time warp can go sample from it, for example. Or if you're doing tone mapping, then you can do your tone mapping. So this is kind of how the GPU actually works. But the problem there is that the fact that the GPU is a tiled renderer is completely abstracted away by OpenGL and Vulkan, which are our graphics APIs, and which is the way that on the CPU we communicate to the GPU. So for example, on OpenGL or Vulkan, there's absolutely no way to say, oh, I want to create a render pass with 5 tiles. Or there's no way to say, hey, the render pass that I computed last frame, how many tiles were there? And did I spend more time rendering the tile or just storing it to memory? Like the entire fact that the GPU is a tiled renderer is abstracted away, which is good in a way because that means that you can take the same Vulkan code and run it from PC to mobile because effectively all of this is abstracted away from you. But if you're trying to get to the next level of application performance, we can't just abstract things away. We need to understand how the GPU works to understand where the bottlenecks are and what you should do to solve them. And so this is kind of what we worked on this year. So what we did is that we partnered with Qualcomm on a library that we call Performance Interface Library, or PIL, which now is being shipped as part of the Oculus Quest OS. So it's the system library, like all the other Androids and all the other system libraries. Now we have a new one called PIL. And what it does is that it's an on-device library that gives us access to plenty of GPU data and GPU counters. So the fact that it's on-device actually was really important, and that was one of our first really hard requirements here, because like historically, there's plenty of mobile profiling systems that absolutely require the phone or the mobile SoC to be plugged into a PC. And this is nice because obviously it's easier to profile something on a PC than on a mobile system. But actually on a standalone headset, that's kind of bad because we really want to be able to run everything on the device so that you can have a heads-up display showing you GPU data and you can run through your game without being plugged in a PC, and you can figure out, oh, when I'm looking in that direction, then stuff gets slower and this is why. So we really wanted everything to be on device. Obviously, that doesn't mean everything needs to be on device. We can then transfer data back to the PC for inspection, but the source of the data should stay on the device. And it gives us access to various types of GPU counters, which I will then explain. And what I like about the fact that it's on device as well is that since everything can be computed locally, it can be quite low friction to get some counters from the GPU. And I think specifically, I think low friction is really important because the more people have access, like the easier it is to get access to data, the more people get access to that data. So not only like low-level rendering programmers, but also higher-level programmers and tech artists, QA, and then effectively it gets much easier for people to really optimize for the platform. So this is a work in progress and is being shipped in the Quest OSs as of like a few versions ago. So what do we actually get access to from this library? So first, we get access to real-time counters. So what real-time counters are is a way, so this is pretty high levels as far as counters go. This used to be able to be accessed through Snapdragon Profiler as well. And what those are is just a query, like a GPU query, such as, like in the last second, how much time did you spend shading fragments? What was the average bandwidth on both read and write? And like how many pixels did you actually compute? Those are the type of real-time counters. This is on device. What we did is that we built a very simple command line interface tool called OVR GPU Profiler. And you can just access it through ADB shell. So when you type ADB shell, you now have a new command called OVR GPU Profiler. And one of its arguments can be -- real-time and then a bunch of real-time metrics. So for example, if you ask for 29 and 30, you will get times shading fragments and times shading vertices. So as an example, this is what you can get. You can go run through your scene and ask the GPU, like, what was the percentage of time in terms of reportation that you spent computing fragments versus vertex shaders? This is quite like basic information, but if you think about it, there's actually no way to know this on the engines if you don't ask the GPU directly. There's no query that you can ask OpenGL or Vulkan that will tell you this. And it's really important to understand because if you need to know what you're going to optimize, well, you should know if you're going to optimize your fragment shaders and your texture samples or your vertex shaders and your actual like vertex complexity. Another thing that this gives you, for example, is sampling types and bandwidths. So as an example, we literally used this like recently to go debug an issue that we had with a UE4 scene, and we could not figure out why. When we looked at that exact scene on OpenGL, it was pretty fast, around like 6 milliseconds. But when we looked at the same scene on Vulkan, it was much slower, around 40 milliseconds. And like we could not figure out why. We spent so long on this. And so we actually then started using this. And the first thing we looked at is the bandwidth. So this is how much gigabytes per second the GPU is reading from RAM. And we noticed that OpenGL was pretty average, around 1 gigabytes per second, but Vulkan was super high, around 8 gigabytes per second. So we were like, whoa, what's happening? So we opened RenderDoc and we could not really figure out what was causing this. So then we looked at sampling types. This is going to tell you how many of your pixels were sampling linear data. So this is just sampling nearest filtering data, so this is just sampling a single pixel, versus linear, so this is sampling 4 pixels, versus anisotropic. So anisotropic can go up to like 70 or 80 pixels if you're really looking at very oblique surfaces. And we noticed that OpenGL, because like what I did is I literally used OVR GPU Profiler, and I had both the OpenGL and the Vulkan readings side to side, and I was comparing them. And I noticed that although OpenGL was 0% anisotropic, Vulkan was 20% anisotropic, which was the bug. I just had a misconfiguration somewhere. And instead of needing to go A/B test and remove all the meshes and figure out that my Vulkan ground mesh had aniso enabled and my OpenGL ground mesh didn't, I could just literally ask the GPU, like, what are you doing? And it just showed me that, which I think is really, really cool. And so this is what I wanted to show here. The fact that it's just on device through ADB shell makes it really low friction. You don't have to restart your app. You don't have to connect to anything else that you weren't already connected to. And in 1 or 2 seconds, you can get access to those metrics. And the fact that it's a CLI also makes it very easy to automate, because you can run this through an automated QA pass for regression testing every night and do basic string parsing to really say, oh, on this build, this was my time shading fragments. And on this build, now it's getting higher automatically. And so you can flag that in an automated way, which I think is really interesting. Since it's on device, we also integrated this data in other real-time tools, such as OVR Metrics tool. So now in OVR Metrics tool, which is the heads-up display that we recommend people to use, you can run through your scene and see fragments versus vertex count. You can see texture stall rates. We created an overdraw metric. So for example, we will divide the amount of pixels, fragments drawn by the GPU in the last second by your screen resolution. And so we can say, for one final pixel, you actually computed 3 pixels, so you have a 300% overdraw, which can help you really figure out like where the issues in your game performance are coming from. So those are real-time metrics, and there's plenty of different ways to access them. But we kind of wanted to go to the next level of really application performance to talk about all the tiling data that I talked about before, and this is what we call RenderStage Tracing. So what RenderStage Tracing is a deeper level of profiling, which has some not insane, but definitely measurable overhead regarding application performance. And what this does is, so you need to ask your application GPU context to enable render stage tracing. So you need to enable render stage tracing using OVR GPU profiler, then restart the app. And then you can do a trace. And what the trace is going to give you is, for the duration of that trace, by default it's 100 milliseconds, but you can change that. It's going to tell you every single surface that the GPU actually computed during the duration of that trace and data on it. So in terms of data, you will get the surface render target size. You will get the color and depth, bit depth, so 32-bit color and 24-bit depth in this case. MSA is 2 here. And you will know the size of the bins, and the number of bins that you needed to compute the entire texture. This can actually be quite useful in trying to figure out the optimal size for intermediate render targets. We use this literally on the Quest OS. We use this exact system in order to figure out what size we should take for the casting subsystem. So when you cast, when you enable casting on your TV or something, there needs to be an intermediate render target that we use for compositing. And we use this to figure out the optimal size that had the less amount of bins, but with a pretty good resolution. And then for the surface, we're gonna give you the repartition in terms of all the time that we talked about before. So here, this is a 5.3 millisecond render with 150 tile executions. And in those 5.3 milliseconds, we spent 0.3 milliseconds binning. So this is a vertex complexity metric that will show you spent 0.3 milliseconds figuring out where all those draw calls are going to the screen. Then we spent 2.7 milliseconds actually rendering fragments and vertex shaders. We spent 0.5 milliseconds storing the results of those computations back to RAM. And for 1.3 milliseconds, well, the app wanted to compute. We were right in the middle of the application iBuffer compute, but Time Warp just preempted us and said, I need to go render stuff to the screen, and so I'm taking your time away. And this is important for you to understand, because this is going to happen all the time. And Time Warp is an essential component of application performance, and now this actually shows you. In my 5.3 milliseconds, I can really not optimize away those 1.3 because this is Time Warp, and this is going to happen no matter what. But obviously, this isn't like the greatest way to visualize this, because this is a lot of data, and you would kind of want to see this on a global timeline, not in like a command line interface tool. And so the tools team actually worked on integrating all this data into the Android systrace, which we call GPU systrace. So this just looks like a normal systrace, but at the top, instead of having just like processes and processes, you have something called GPU timeline, which is the topmost level like subsection here with this huge purple outline. This is an iBuffer compute of a UE4 application. And there's a few things I wanted to show on this screenshot that I thought was really interesting. So the first one talks about what I talked about before, which is the CPU and the GPU, how the CPU and GPU work together. So at the bottom part here, there's this green section, which is actually an A-trace section I added to UE4, which is the Vulkan end command buffer section. So this is actually the CPU execution of the end command buffer call to the driver. And what end command buffer does, end command buffer and qsubmit, is finalizing all the draw calls and then sending them to the GPU. And as you can see, exactly as I was talking about before, when we're done with CPU execution, so when we actually execute the commands that send all the draw calls to the GPU, As soon as those commands are done, then the GPU starts computing, which is why you can see that the purple section, which is the actual GPU iBuffer compute, starts right after end command buffer on the CPU side. So this makes quite a bit of sense. When you look at the amount of surfaces, we can see there's multiple surfaces. There's the big purple one, which is the iBuffer, and so this is obviously the most expensive one. But then if you have other surface executions, you can also see them here. So at the end, we can see there's another surface, which if we were to zoom in, would show a pretty low draw call count, 1024 by 1024 render, and this is the UE4 heads-up display. So when I typed stat FPS, and so I could see on the top right of my UE4 render, my frame count and my vertex count, and this is that time. And then the last thing that I wanted to talk about is the stale frame, early frame metric. This is actually how it's being computed. Time warp, and so the runtime absolutely needs to know when your application is done rendering. Because at some point when time warp is going to go, it needs to know what is the latest frame that we can actually use for time warp rendering. What is the frame I should really start drawing onto the screen? And so how we do this is that when you call VR API submit frame, which is the call to say I'm done with my frame on the CPU side, what we do internally is that we enqueue a GPU fence onto the command stream, and we create an asynchronous thread that's going to be waiting on that GPU fence. And that way we know when you're done rendering, and we can tell time warp, but that frame is now done. You feel free to sample from it without any artifacts. And we can also see that thread here. So that thread is the red section here called fence checker wait. And so this is just a thread sleeping, waiting for your GPU to be done. And you can see as soon as the last section of that GPU frame is done, fence checker starts waking up. It sends a command to time warp saying this frame is done, and now and then the thread section fence checker wait just dies. Which you can literally now visualize here. And I think this is actually really cool because it shows people how the underlying platform works. And so for example, if you had a stale frame, you could literally understand why it happened by looking at this. I did want to talk more about time warp. Because we can also visualize time warp in GPU systrace. So you can notice that in this huge purple iBuffer execution, if you were to zoom in, you would see two stages called preempt. So this is actually when time warp started executing. And exactly as before, time warp doesn't execute out of the blue. There's also CPU executions related to this. And so if you were to look at the time warp process, you would see the two trace time warp slice executions here. And exactly as before on the application side, you can see that effectively as soon as time warp slice is done, so time warp slice is the CPU side of time warp that just looks at the latest frames that were done and then sends the GL draw calls for time warp to execute. As soon as that's done, then the GPU starts waking up and saying, all right, I got to execute time warp now. And so this is why when time warp slice starts being done, then the preempt stages on the GPU start waking up, because this is CPU to GPU exactly as we talked about before. And you can notice that there are two silver preempt stages around 7 milliseconds away from each other. And the reason for this is because on Oculus Quest, we have what we call a rolling shutter display. And so we don't have a single time warp execution per frame. Time warp is split into two, so top part, bottom part, time warp, top part, bottom part. And so every 7 milliseconds, we're going to execute half of the screen effectively. And you can now visualize this. This was a question we had from plenty of devs, and now you can literally figure this out on your own by looking at how the preempt stages work and how they interact with your application. The last thing I wanted to talk about today, which is the more a work in progress, is draw call metrics and draw call counters. So we had real-time metrics before, right? So all of those percentage of time spent on fragment versus vertex counts, bandwidth, texture stall rates. Although we have them at a real-time level for the entirety of the GPU, we can also ask them on a draw call per draw call basis. But those don't really make any sense to show you on a command line interface tool. Because if you had 200 draw calls, you would have a gigantic output on the command line interface with absolutely no way to link them to actual draw calls. This doesn't really make any sense on a text. So what we did is we integrated this into our RenderDoc fork that we released recently called RenderDoc for Oculus. And how this works is in RenderDoc for Oculus, if you go to the performance counter selection tab, which existed before, on Quest devices, you only had a single performance counter selection, which is not much of a selection, which was GPU duration. So that was just asking RenderDoc to put timestamps around your draw calls and give you the draw call time. But now, if you go on the Oculus tab, you have around 45 new metrics, such as here clocks, vertex fetch stall, texture fetch stall, and plenty of others. And so you can select the ones you want. and then you can press the sample counters, which what that's going to do is just replay your frame and ask PIL to go attach itself to RenderDoc and measure for every draw call plenty of all the counters that you required. And here, for example, on my Vulkan UE4 draw calls, I can visualize for every single draw call the clocks, because I only ask for clocks. So this has quite a large overhead, but the interesting thing is that the delta is still valid. So although you probably shouldn't believe those clocks as like those clocks is literally how my app is going to run, if a draw call has 3 times more clocks than another draw call, the delta is still valid. And so you can still, from this, gather data that you can use for actual asset changes. And this is how we want you to use it. So this is still a work in progress. There's plenty of issues, which is why, for example, we only shipped this on Vulkan so far. But we really believe that this is what's going to help you like achieve the next level of application performance without spending months of A/B testing. So that's pretty much it for changes on GPU profiling. And yeah, before leaving, I just wanted to say that this was a huge like cross-functional effort between various Oculus teams, such as the tools team, engine teams, and OS teams, but also mainly Qualcomm, which really helped us there. So yeah, thank you everybody for the work. See you around.